Assalamu alaikum everyone, it's Mr. Fahad back with another math lesson for grade 12. We are at the fourth lesson, continuity and its consequences. Now, by the end of this lesson, we should be able to use the continuity properties to study the continuity of a function or composition of functions at a given point. And then we will learn about the intermediate value theorem and how we use it to approximate zeros of a function. Well, a continuous function can be drawn with a single unbroken pencil stroke. So this is the basic idea of a continuous function on any interval. Okay, let's start with the definition of a continuous function at a point. So if we have a point A and the function is defined on the open interval containing this point, we say that f is continuous at A when the limit of the function equals the image of the function. So again, when the function value is the same as the limit value. Otherwise, it's said to be discontinuous at point A. So for a function to be continuous at x equals A, the function must be defined, and then the limit must exist, and then the function value is the same as the limit value. All right? Okay, so looking at the first graph, you can see that the function is not defined at A. Okay? This means that the function should not be continuous. Even if you have a limit, again, you need three conditions. One of these is the function of A should be defined. Moving next, the function here is defined and the limit is defined, but you can see the values are different. So if the function value is not the same as the limit, we say that the function is not continuous. Now with the third graph, f of A is defined. You can see a closed point here, but the limit from the right and the limit from the left is different values. So the limit does not exist. This means that the function is not continuous. And in the last example here, when looking at the limit, I can see that the limit does not exist. So this means that the function is not continuous. Again, you need the function value to be the same as the limit value. Well, the first graph, it's called removable discontinuity because you have a hole in the graph and you can just fill it to fix the discontinuity. Here also removable, and here you have jump discontinuity, so it's not removable. You can't fix this without changing the original function. And here also you have an asymptote, so infinite discontinuity. So we have this function and we've been asked to determine where this function is continuous. Well, first of all, any rational function is continuous at all the domain except at the zeros of the bottom. So basically, rational functions are undefined at zeros of the denominator. If we took the bottom, set it to 0, we can see that x equals 1. So f of x is undefined at x equals 1, and therefore it's not continuous. Again, it's continuous where the function is defined. And if I try to graph it, the best way here is to try to factor it out and cancel out the common factor, because we have a removable discontinuity, meaning that when you substitute 1, you'll get indeterminate form. So by factoring, you can make the function as x plus 3. All right? So this is defined for all real numbers except at 1. Again, because 1 is the 0 for the original function. So you can see there's a hole at x equals 1, and the function is continuous for all real numbers except at 1. Now, what if we've been asked to extend the function f to make it continuous everywhere? So we know that the function is undefined and it's not continuous, but at the same time, the limit does exist. This means it's a removable discontinuity. So we try to evaluate the limit at x equals 1 by factoring. So if you cancel out the common factor, you'll be left with x plus 3. At 1, this equals 4. So to remove the discontinuity, we will define a g of x where the function is the same everywhere except at 1, but at 1 we will make the function equals the limit. So the function equals 4. Or simply it will be x plus 3, which is the graph with the hole. Now with the hole filled, this means that the function is continuous for all real numbers. All right, here's a question. Please pause the video. Try to do the same as we did. So in this question, they ask us to determine whether f of x is continuous. If possible, extend f to a new function that is continuous on a larger domain. Meaning, if it's removable discontinuity, fix it. Let's solve the question. So the first thing is to check where the function is undefined. We pick the denominator, set it to 0. So f of x is undefined at x equals -2, therefore it's not continuous. But the limit of f of x does exist, because if you substituted -2, you'll get 0/0, the indeterminate form, and we can evaluate it by taking the limit, factor it out, and then cancel out the common factor. You'll be left with x minus 1. At -2, this will equals -3. All right, so to remove the discontinuity, basically we need to fill this point, and therefore we can define a function g of x such as it's the same as f of x for all real numbers except at -2, and at -2 we will fill it with the value of the limit, so -3 at x equals -2. And this will be a continuous function. That's it. All right, so here's another question. You can pause the video and try to solve it. Well, first thing, to determine where f is continuous, we need to get the zeros for the denominator. So set the denominator to 0. This gives us x equals 1 and x equals -1. So at these 2 points, the function is undefined, therefore it's not continuous. So at x equals 1, the expression can be factored out, and these two will cancel out. You'll be left with 1/x plus 1. Substituting 1, you'll get half. Therefore, it's removable discontinuity, since the limit has a value. At x equals -1, if you substitute -1, you'll get 1/0, which is infinity, so the limit does not exist. We say it's non-removable discontinuity. Now, if we try to simplify the function, it can be graphed as 1/x plus 1 for all real numbers except at 1. Now, to extend the continuity at x equals 1, we can define g of x as 1/x plus 1 for the whole domain. This means that g of x is continuous for all real numbers except at -1, because it has an asymptote at this point. So let's talk about continuity of functions. Theorem 4.1 says that polynomials are continuous everywhere. Sine, cosine, tan inverse are also continuous everywhere. The radical of x to odd power is continuous everywhere. But if it's even, then it's continuous for all x larger than 0, so for positive values. Len of x, continuous for x larger than 0, because the len function and the log function is not continuous for negative values. And also sine inverse, cosine inverse, continuous on its restricted domain. You can think of it as the range of the original sine and cosine functions. Moving to the next theorem. So if we have two functions continuous at a certain point, the sum of these two functions is also continuous at this point. The multiplication, the division is also continuous. Of course, g of x should not be equal to 0. On the next theorem, we are interested in the corollary, which says if g of x is continuous at a and f is continuous at g of a, then the composition f after g is continuous at a. So again, the composition of two continuous functions is continuous. Let's talk about continuity on a closed interval. According to this definition, if f of x is continuous on the open interval AB, then we can test the points, and if the function equals the limit at the starting point from the right side, okay, so from inside the interval, and the function at the end point equals the limit from the left side, again, we are only checking for this side inside the interval, then we can say that the function is continuous on the closed interval AB. So that's how we check for the continuity on a closed interval. Example, determine the intervals where f is continuous for this function. Now, first of all, let's see where it's defined. To find the domain of f of x, take what's inside the radical. Since we are dealing with a radical, it should be positive. Solving this inequality, let's solve the equation. X equals plus or negative 2. And therefore, I can see the inequality solution is in between. So here's the interval where the function is defined. You can see it's defined for the closed interval since f of 2 and negative 2 equals 0, which is fine. But the function, we say it's continuous on the open interval. Now, to prove that it's continuous on the closed interval, we should follow the prior definition. We test the endpoints, so f of negative 2, which is 0, the limit at negative 2 from the right side. Again, we are looking at the starting point from the right side, and the limit equals 0 by direct substitution. Let's check the other endpoint at negative 2. F of negative 2 is 0. Now the limit is also 0 from the left side. So the limit from the left side by direct substitution equals 0. Therefore, we can say that the function is continuous on the closed interval. Now, in this example, they ask us to determine where f is continuous. You can see the function is piecewise defined function. We can see that the function is continuous for all less than 1, and it's continuous for all larger than 1 because it's polynomial expression. Now, we will check at the point x equals 1. Now, the function is where the equal sign is, so we will substitute with x squared, which is 1. F of 1 is 1. And in order to find the limit from the right side, we will substitute with x larger than 1, and this is 1. With the left side, we will substitute with 2x, and this equals 2. Therefore, the limits are not the same, and we say that the limit does not exist. And this type of discontinuity is called jump discontinuity. It's non-removable because the limit does not exist. And looking at the graph, I can see that the function is continuous for all real numbers except at 1. In this example, we need to determine the values of a and b that makes the given function continuous. Pause the video, try to solve the question, and then check your answers. Let's do it. So for the function f of x to be continuous at 0, this means that the limit from the left, from the right must be the same, and it must be exist, and it should equals the function, right? So since the limit from the left and the right should be the same, we will try to evaluate the limit for these two expressions. Again, we started with this because we can evaluate the limit from the left side. Now, in order to evaluate this expression, we will use the rule of sine x over x. So the limit when x approaches 0 of sine x over x is 1, because again, we are looking at the limit at 0. Therefore, it's 2 times 1. On the other side, we have b cosine of 0. Cosine of 0 is 1. Therefore, b equals 2. And now, in order to find a, I know that for the function to be continuous, the limit must be the same as the function. So f of 0 is a, and the limit is 2. Therefore, a equals 2. Moving to the last part of the lesson, with the intermediate value theorem, it says that if you have a continuous function on the closed interval, and w is in between f of a and f of b, then its x coordinate must be in between a and b. Well, we are interested more in the corollary of this theorem, which says if you have a continuous function on a closed interval a to b, and f of a and f of b are different signs, then for sure you will get a zero in between a and b. Okay, let's try to understand this corollary more with an example. In this example, they ask us to use the intermediate value theorem to verify the function has a zero in the given interval. Then we need to use the method of bisection to find the interval that has the length 1 over 32 that contains the zero. So in order to solve the question, we need to check whether the conditions apply for this function. Now, this function is polynomial, so it's continuous everywhere. And then f of 2, we can substitute using our calculator. It will be -3. F of 3 is -2. And since they are different signs, then we can apply the intermediate value theorem. So it must have a zero in this interval. So if you graph the function on Desmos, you can see there's a zero in between 2 and 3. Now, we will use the method of bisection to approximate where this zero is, and we will give the approximation to a small interval of the length 1 over 32. Let's plot it on a number line, and you can see the initial point 2, the end point is 3, and I have the f of x values down here. Now, in order to approximate the zero in a smaller interval, first we need to take the midpoint of this interval and then check whether f of x for this point is positive or negative. And then we keep on squeezing the interval in between the different f of x signs. So the midpoint here is 2.5. You can find it using your calculator. So using our calculator, if we wrote the expression of the function and we try to evaluate at x equals 2.5, I can see the result here is -0.75. Continuing with the method of bisection, I need to focus on this interval since f of x here are different signs, is 2.75. Now I moved it to the right to fit the other points in here. Now to evaluate the function at this point, we use our calculator, and this equals a positive value. Since f of this point is positive, I will be looking at the zero in the interval in between the two different signs. So the midpoint in between these two numbers, using your calculator, it will be 2.65 in our calculator, and this equals a negative value. Now we will keep on bisecting the intervals with the different f of x signs. Now calculating the midpoint, it will be 2.6875. Substituting the value in our calculator, this gives us a positive value. So we have to look again in this interval and the midpoint using our calculator. And then substituting the midpoint, I will get a positive value. So I know that the zero will be in between the different signs of f of x. So this makes the zero in this interval. The reason we stopped at this interval is because of the condition in the question. They ask us to do it to this accuracy. So the length of the interval must be 1 over 32. That's it. So now I know that the point of intersection is in between these two values of x. So this question was an application for using the intermediate value theorem and the method of bisection to approximate the solution for a function. That's it for today. Thank you so much for watching.